Yesterday, we talked about, well, artificial intelligence approaches. As my course is progressing, and believe it or not, we're still kind of in the content range of the first class. So, well, you can see that it's very information packed. But, well, again, the course is from Harvard. If you want to access it, it's free and online. You can access it in the description down below. But we learned that, well, artificial intelligence has a kind of approach, and we learned that one type of approach, in this case, there I don't think he mentioned the name, pretty much because I think there is no name. It's just pretty much something that it was thought up because it's very simple indeed. Pretty much, I look a node, I well explore it pretty much. I see if it's my goal state. That's my exploration of the goal state or of the node. Sorry. I span my frontier, which is the direct connections, just the direct connections from my node, and well, because of that, it was very simple. Really, you just explore each node individually. The problem is, since we have a branching path after a second node, it was purely by chance that it could get stuck there. So today we set out to fix this problem by making somehow, or in this case by creating an entirely different set of informations. We now make our computer remember what it did and remember what it explored, so it can pretty much go back. I'll show exactly how this happens. Now, I have my previous approach here, and you can see it was quite simple. I started with frontier, containing the initial state, and then I will always repeat. If my frontier is empty, then there is no solution. Meaning, well, if there's nothing in the frontier, pretty much meaning that there's no solution. So I need to expand this. So I run this again. I remove a node from the frontier, which in this case, like right in the right first ever node, we don't do this. And so you can understand this better. Beside this bunch of words, you can check out my last video where I don't just go in detail, but I kind of show you a physical representation, not physical like this, but I show you on a PowerPoint slide, like any good talker, pretty much a good speaker would do. So pretty much, if you want a simplified version, ours had a big problem. It got stuck, just as I said. So let's use these chocolate footballs, which I found some reason it was extremely tasty. I have a benching part. Let's actually use my hands. I think it's better just put nodes. So I have a branching path from here. So this is one node, and there's another node here, the one I want to go, actually want to go, and there's a path here, node here. Now let's actually between those let's add another one. So I have one here where I came from, one here, which is where I want to go, and one here and one here. The problem with the last result there is that, well, if we accidentally got to the wrong place, that would pretty much means that we cannot go back and the problem is over because it can't remember. So that was the biggest drawback, I would say, because, well, it wasn't remembered. Again, if you want to see a better representation, watch the last video. I go in more detail than that. So anyway, this was my last approach, my old approach, primitive approach. Now we have a new approach. Now I have again this new approach, and it starts pretty much with the same thing. It's actually very similar. So let's read out. Start with frontier that contains initial state. Okay, that's easy. You start with the empty explorer set. Now this will become important. The explorer set is my memory here. Explorer set is the nodes I already explored. So if, well, if I already visited it, I couldn't go back, because even though I personally would think the biggest problem is getting stuck on a branch of nodes that has a dead end, It does not mean it's the only problem. Another problem is that it has a defect. Example, taking these two chocolate balls. Let's say actually between the two chocolate balls, I have a third here, a goal, which is here, is orange one. Now I start in the black one, and I can go and for some, and I have a pretty much a double connection where I can go from the black to the red or to the red to the black and during the football. And my goal is orange. And since I'm not remembering exactly what I do, that means that I could go to the to the red ball, to the red orange ball. Actually, it's yeah, it is orange. It is red, but let's take a better one. This is yellow, so it can better be recognized. So I go to the yellow one. But here's the problem. Since I'm not keeping track of, I could simply go back to the black ball and then again to the yellow ball. And I could go on and on without ever achieving my goal, since it's pretty much random. Now with the export set, I remember that I already got to the black ball, so I don't need to go back. So I just export the orange ball. So it's extremely important, this export set, and we actually have one here. And we started pretty similarly. Now I repeat forever. If the frontier is empty, there is no solution. So there is no line here. I remove a node from the frontier, pretty much meaning I explore this node, or I will be inside this node pretty much now. If now my node that I removed, which is now the node I am looking at pretty much, is the goal state return solution. Since my goal state is pretty much my last, this probably won't happen in the first thing. Whoops. It probably won't happen in the first test, first try. So I will add then the node to the explore set, meaning I well is actually the last rule will explain this better. Since I expand my node, meaning I will see what I can do, the connections in from the node, and result the node to the frontier if they are already in the frontier or the explorer set. Meaning, well, if I have here, for example, I go back again. Let's have the chocolate balls here. I actually have a bucket of them right on the side. Really easy to eat and used to explain. So if for some reason I go here and let's take a fork. That's malabarism. You can see here. So if I explore here, for example, and let's say, well, I will actually later. Let's just use the two hands. You can see here. So let's say I want to explore two places here, and I need to go back. Let's stop using the balls. I want to go back for some reason, but I already have it memorized or on the explore set. That pretty much means that I would just ignore it and won't go back to the place again. So I will use a system that uses this. And this system, the most important, I probably wouldn't call it the most, but extremely important thing that I need to do is change my frontier so it works like a stack, because it's very important how we remove a node from this frontier. Last time was random. It could be the first, could be the last, but now I'm using a stack approach. And well, I clicked too fast here, but a stack approach pretty much means that I will lasting first out data type. Pretty much means that the last that enter will be the first to let go. So again, in my frontiers, I remove a node from the frontier. Now, in this case, the first that got in, remember, just like a stack. In this case, I'm holding my hand, so I could remove the last one. But logically, I would want to remove the first one. So that pretty much means that's the stack approach, because the first that got in, the last that got in will be the first to be removed. So, well, we can now start exploring this approach. better. Now I have a simple part here. Just like the last time, I began from A and I want to go to E. But I have now this set of new rules. So if they're a little bit smaller than the last time, I couldn't make it fit. So we can start again. I actually put here, but we pretty much start with the frontier being A. So I have my frontier A, and I also have, which now here my frontier A, and I need to explore it. And now what we do with the A frontier? Well, we look here. I remove a node from the frontier. That means I will explore the next one. Since there was nothing, or in this case, there was nothing because I pretty much I put it like a blank state just to see the challenge here. But here I will start to actually explore. So now A is part of my explorer set. It's here in yellow. Now let's see if now I need to try to now expand my node. By expanding my node, I am having this connection you can see here. And also, though it didn't use in the course, I did the one that has the both arrows, so you can see there won't be any changes. So I expand my A node, and now my frontier is B. Okay, so I just expanded. If the frontier is empty, then no solution. Okay, it's not empty, so there's still a solution. I remove a node from the frontier. Now I explore it, and now it makes part of my set. And you can see even I have a arrow pointing to A, it will not be able to be in the frontier. After all, it will not be in the frontier since, well, it is already on the explorer set. And you'll be in that way. Since we don't have any rule that says we need to remove my from the explorer set, it is there forever. Okay, so now if my since A is not my goal, neither is B, I need to expand it again and add it to explorer set. Now I have C and D as my explorer set. And there is a very interesting point here. After all, we need to remember the stack approach, meaning, well, I need the first in is also the first out. Sorry, the last in is the first out, meaning D. So in this case, D will become my explorer, and I will add it also to explorer set, and I will just then expand it again, meaning now F is in the frontier, and since F is the last editing, it's also the first to be outed. So again, it will go to the explorer set. Now, since I have reached a dead end, there's nothing more to the frontier. In this case, there is something more to the frontier, but there is nothing more to explore. I mean, I cannot expand it. So I will remove C from the frontier and make the explorer part. So I add C to the expand portion. So okay, now I'll expand my node, meaning E is now in the frontier, and since the E is the only one and also the last one that entered, I will make it my new explored set. And well, now I have reached my goal state. Now this is my solution, and my solution really looks interesting because you probably can see that, well, every single node in the explorer set, absolutely everything. I explored every single possibility, and you can also see, especially, that I first searched the deepest part here, which is from ABDF, which is the deepest part. Then I got back and from here to C, and then I explored here. Well, this actually has a special name. It's the Deep First Research. Well, meaning that, well, I going deepest I can. So let me see. It's a search algorithm that always expands the deepest node in the frontier. Pretty much meaning I will explore one portion and then explore another. If I have again multiple paths, I will expand the deepest down or from all the way down. Then I will go back if it fails. So I will expand every single nook and cranny of, well, one path. Then I will go back to another, or every time it separates at least. So it's very interesting. But since, well, we are already making a video about it, I decided I'm gonna actually show a different approach. And this approach is the breadth first, which is extremely similar, but, well, just changes one thing. It always expands the shallows of the frontier, meaning that I use a different way. Because what made it the last one, specifically the deep or the depth first search, is that the way I control my frontier, and I'll pay close attention to it, because that's pretty much what defines it. The explorer said, of course, it's necessary so you can remember not go back, but the most important part here to defining the deep first or shallow first research or search algorithm is how my frontier is manipulated. Since last time it was the last in, first out, now it's different. It is first in, first out data type. So the first who got there will be the first to leave. If I take my chocolate balls in a new example again, and I do not accidentally throw them on the ground again, they actually fall in my hand. Uh, in this case, in this Q case, I will remove from here, from the first, from the stack, from the right, from the um, bottom of the list. So you can actually see the names has a pretty good way to define things. Stack, because when you stack things, you usually, well, get then the last one you added, you remove them the first. But in a queue, it was more of a line. So in a situation like a not line like this, you will probably remove the first one who got in to then remove the second person who got in. So very interesting name-wise. That pretty much meaning that the name actually makes sense, which is interesting. Actually, since it's programming is pretty much a language, usually the names make sense in the situation. Okay, so now let's explore this situation here with a shelf. Again, a shallow way to explore. Again, my first frontier is a nothing different here, and so it becomes my first explore set. And well, things do not become different with B. After all, now I will communicate with B. After all, I'm going to expand A, add B to the frontier, and then I'll remove B from the frontier and add it to the explore state set, because now I look in B pretty much. Now the interesting part comes. I add C and D to my frontier, and well, since it's a queue based frontier, I will first explore C. So I first go there, go to the C, goes to C, sorry, the C node, and I will then expand C, adding E. But since D was first at E, I will then explore it again. Now I explore D, and I will add F to the frontier. But I will not explore F, since my now goal is E, or in the case, sorry, my last, okay, yeah, it is my last, but my next frontier is E, which, well, I already, since my goal is a go state, a return solution. Now the solution is very different. Is A, B, C, D. You can see it kind of explore this way. Since here, if from what I understand, it pretty much means that the deepest, the last one we saw, pretty much looks at each line individually, all over, and then it eventually, when it's struck gold, pretty much, you will be able to find the solution. Well, it's very interesting. I would say has, of course, the drawback. I would say you have a lot of things to explore. I think actually this problem applies to both. But since you are adding, every time it separates, you will explore one point specifically, the deepest you can go. And if you hit a dead end, you will go back and explore the other side pretty much. In the deepest, the shallowest, you will gradually doing things. So, for example, you can see from A to B, of course, but then B to C and C to D. And if my last solution wasn't E, then we go E, then to F. So you pretty much do a zigzag in this sense. You go one. Now, again, this is pretty much has a problem, because if you have a lot of things to explore, it will take a lot of time to get deep. But you need to, if the solution is not that deep, then it's much faster. Unlike the deepest way, if the solution is deep and, well, it is the right arm you explore, it will be fast, or much faster at least, than the shallows note. And I now have a very good question. What do you think is the difference in an actual situation? For example, if you want to solve, per se, a puzzle with this situation, what do you think they would be? Now, leave this comment down below. In fact, next time, which actually is not tomorrow, but on Sunday, uh, yeah, I think Sunday, yeah, Sunday, sorry, Sunday, Monday. On Monday, I will have this response to you. But please still leave them the content, those comments down below, because helps a lot. And if you want to learn, I think this engagement is very helpful for you. After all, uh, you probably have enough information, or yeah, I think I would say that you can try to figure how it would work. And it would be very interesting as a thought process, because that's pretty much how the artificial intelligence will behave. But that's enough for today. If you like this video specifically, like it, and if you want, and especially if you want to understand much of the things that happened, watch last video, and I think the video before that, because yeah, that's the last video, the video before that, so you can understand better the process. It's a new series, so I promise there isn't much content yet. The course is huge. It's spanning 7 weeks, with each class being 2 hours long. So a lot of things, and this content, these three classes, the 3 videos I did, are pretty much covering the, well, first, the first hour or so of the first class. So definitely there's be a lot of things to explore, how artificial intelligence work, programming, etc. So, well, that's it. Subscribe for more, and, well, hit the bell if you want to receive a notification when it's my next video. And that's it for today. Goodbye.